Okay, so now I would like to discuss with you a separate topic. This is about some applications of tunneling. Tunneling is quite a signature of quantum mechanics because classically a ball hits the wall and it will bounce back certainly, 100%, okay? But quantum mechanics, due to the wave nature of particles, just like EM wave, it may go through a glass of water and then through the glass to the other side, okay? So that is just the wave property exhibiting some effect. I understand that if you took quantum mechanics 1 last term, you have seen the standard treatment of tunneling problem through a barrier, etc. Okay, I know that. I read the notes yesterday, so therefore I try to motivate the problem, remind you some of the essential idea behind tunneling, and then discuss its applications. So that is the idea. For this part, I will go like as if it is a seminar. I will not go through everything in the standard details as it are the topics that we have done so far. So let me motivate why we want to look at this part. In particular, the whole quantum mechanics started with a key experiment using alpha particles to hit a thin gold film, and then some of them turned back nearly 180 degrees, and then Rutherford said, for an atom, the positive charge come together as a point particle that nowadays we call the nucleus. Okay, so we have this alpha particle decay very early on, okay, in the development. But in order to understand why we have alpha decay, actually we have to wait about 30 years or so, 25 years, until early 1930s, late 1920s to early 1930s, where we have quantum mechanics. It relies on tunneling. So first motivation, alpha particle tunneling, decay. That means from the nucleus, we see alpha particle coming out. How come? So a nucleus is of the size 10 to the minus 14 to 10 to the minus 15 meter, femtometer. Okay, that is the ballpark range of a nucleus. Or someone will call it a Fermi. A Fermi is 10 to the minus 15 meter. Okay, to recognize the contribution of Fermi to nuclear physics. Inside the nucleus, we know that there are many proton neutrons. Alpha particle from high school, you know that it is a collection of 2 neutrons, 2 protons, so-called helium nucleus. Okay, and then it will come out. So that is the phenomena, alpha decay. The question here is, let's look at some numbers and then we know what really is the question. Here, there's an analogy about lifetime, okay? Earlier, we talked about lifetime, excited state, emit a photon to go to the ground state, and then we have this number of atoms in the excited state decay with time. Therefore, there will be an exponential decaying number in time, and we call this 1 over lambda the lifetime. Okay, we did that. We know how to calculate it. Similarly, in nuclear physics, you have this nucleus here that can undergo alpha particle decay. So you can think about it, you have a collection of nuclei, and then it is a probabilistic event So the number will decay in time just like our excited atoms formula. Therefore, there will be a lifetime. This is 1 over lifetime, okay? So there will be a lifetime associated with the nuclei that can undergo alpha decay. And here is some data. These are the nuclei that can emit alpha particle. They undergo alpha particle decay. And here are the kinetic energy of the alpha particle coming out. Okay, now Rutherford used this alpha particle to hit at the gold thin film. Okay, so this is the alpha particle coming out with this MeV scale going in. Okay, now look at this number, rather boring. Now this is MeV, 10 to the power 6. Okay, MeV, nuclear physics scale. And then all of them are just 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so you see, 4 to 9 MeV. We realize that the kinetic energy do not vary by much across different nuclei. However, if we look at the lifetime or something called the half-life, they are related by log 2 to the lifetime. And then look at this number. This number goes from, this is microsecond, 10 to the minus 6 second, to thousands of years, even to billions of years. That is longer than the universe lifetime. Okay, that means you keep on waiting. You occasionally you see one or something like that. Okay, so the point is, from many nuclei, the alpha particles that comes out do not vary much in terms of kinetic energy. The energy comes out. Okay, however, the lifetime vary by a big amount, many orders of magnitudes. So that is the phenomena. How come? Okay, and this is related to tunneling. So let me motivate the problem a little bit before we take a break. So the idea is as follows. We have the nucleus, and inside which we have a alpha particle. Sometimes it wants to come out, and occasionally it can come out, okay? So after it comes out, we have an alpha particle which has plus E charge, and then the daughter, the remaining thing, has 2 protons come out, so you set -2 charge in the so-called daughter nucleus. In this situation, if their separation is R, they repel each other. So this is plus charge, this is plus charge. Once the alpha particle get out of the nucleus will try to repel it away, okay? So in terms of potential energy, we have this Coulomb repulsion energy. This is a plus repulsive 1 over R Coulombic. Okay, so this is potential energy. If I plot it out, that is to say, when the alpha particle is already outside the nucleus is of this size, so I draw it out to somewhere here. If it is already outside the nucleus, it sends a repulsion 1 over R. Okay, so this is what I want to plot. However, when it is inside, before it comes out, we have nuclear force. This nuclear force, obviously, is attractive. Otherwise, nucleus will not exist, right? So this is a different type of force, not gravitation, not Coulombic. This is more microscopically is called strong force. But at the nuclear physics level, it is the nuclear force. There's some technical difference, okay? But I don't want to get into it. All in all, what is happening is that neutron, 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 proton, proton, proton has an additional force to bind them, rather strong, okay? And we know that it's short range for the reason that the decay comes out, it will repel out. It will not attract it back. If this nuclear force is longer range, it could get the alpha particle back into the nucleus. It doesn't happen, okay? So for that reason, when the separation of the alpha particle from the nucleus is within this range, meaning this alpha particle lives here temporarily, okay? It is being bound to the nucleus. And we know a quantum well will bind. So I will draw a well here just as to trap the alpha particle, okay? And we also know from data, the alpha particle that comes out is of the order MeV. So the situation will be something as follows. The alpha particle living in the nucleus will be somewhere of this energy, okay? So it may be moving around within the nucleus, but it sees a barrier, this barrier, okay? So maybe it keep on trying very hard, bounce back very often, but occasionally, due to tunneling, it will come out, and we measure this few MeV kinetic energy, okay? So that is the motivation. And now, look at what it has to do in order to tunnel through, okay? Now, if this particle has a slightly higher energy, the deficient in energy, I mean this one, okay? The deficient in energy relative to the top of the barrier will be smaller, okay? And from tunneling result, if you remember what you got last term, the tunneling will be very sensitive to two parameters. One, how far it has to go through in the barrier, okay? Now, if the energy is that lower, it is that far. If the energy is slightly higher, it is a shorter barrier to go through. Secondly, is the deficiency in the energy relative to the top of the barrier, okay? Now we have some sense already. Even if the kinetic energy vary by a little bit, these two parameters can vary by much. Namely, how far it has to tunnel through and what is the deficient in energy, okay? So it started to make sense to consider tunneling as the mechanism of alpha particle decay. So the next thing I would like to remind you of some knowledge or basic knowledge about tunneling, okay? So starting here is something that you know. So at this point, let us take a short break, a few minutes, and then I will start from here again.